In this video, we're going to look at measures of dispersion. Dispersion is another way to say spread, so sometimes you'll hear this referred to as measures of spread, but it tells us the variability of the data. It tells us the spread of the data and how the data varies about the mean or the average. The range and the standard deviation are measures of dispersion, and we're going to discuss those in this video. The range is the difference of the dataset's highest and lowest values. It tells us the total spread of the data. And the way we find the range is we take the highest value and you subtract the lowest value. So if I had the set 1, 3, 7, 12, and just those four values, the range would be the highest number, 12, minus the lowest number, which is 1, and so my range is 11. A common mistake that people make, and I hope that you don't fall into this, is that when they say range, they think of it as like in conversational speak when you talk about things like age range. And so they think of it as like the range of 30 to 34. And they try to write the range like this. That is not what we're discussing when we're talking about the range when we're looking at statistics. In statistics, is the single value that tells you how much your data is spread. Okay, so this data set here is spread over 11 values. So this number is the range. This is how you calculate the range. You subtract the highest number, 12, minus the lowest number in this case, which is 1. So please make sure you understand that the range is a single numerical value that represents the total spread of the data set. In these next examples, I'm going to ask that you actually calculate the mean, median, mode, and mid-range on your own. That's a good review of our measures of center. We're going to just calculate the measures of dispersion. Then I will pause, and I recommend that you pause, calculate the measures of center, and then compare. So for this first set, our measure of dispersion is our range. That's what we're looking at. And we're taking our highest value 9 and subtracting our lowest value 1. 9 minus 1 is equal to 8. Okay, then we have the next one. Same thing. The highest value is 9, the lowest value is 1, and the range is equal to 8. And then look at this one. The highest value is 9, the lowest value is 1. This is equal to 8. So now I'm going to pause and I'm going to fill in the mean, median, mode, and mid-range. I'm also going to set up these number lines below, and then we're going to compare these three sets that have the same ranges. We want to see, are their measures of center the same? So you'll see that for all three of these data sets, we have the same median, the same mode, the same mid-range, and the same range. We also have a very similar, if not exactly the same, mean. Two of the sets have a mean that is equal to 5. One of the sets has a mean that's equal to 4.8. Now, what does this mean? Looking at this, you might say that set 1, the first one, and the third one, I'm going to circle both in purple. You might say that those two sets are the same. They have the same mean. They have the same median. They have the same mode. They have the same mid-range. They have the same range. You might say that they're the same, but if you look at them, you can clearly see that they're not the same. Look, this one had 4 5s, and this one had significantly more than 4 5s. There's 1, 2, 3, 4, 5, 6, 7, 8 5s. So we can't only look at these measures of center and measures of dispersion to have the full picture of what's going on in the set. So we cannot make claims that if a set has the same mean, median, mode, range, and mid-range, that they are the exact same set. That is not necessarily true. The second measure of dispersion we're going to discuss is the standard deviation, and this measures how much the data actually differs from the mean. It's symbolized by either the letter S, which represents the sample standard deviation, or the letter sigma, which is a Greek letter, kind of looks like a little cursive O. That is for the population standard deviation. We're going to assume that all of the data presented in this section are coming from samples, so we're going to focus and use the symbol S to represent the standard deviation. If there's a lot of variability of the data about the mean or around the mean, then we'll have a larger standard deviation. Let's consider the example they presented in the book. We have two sets. The first set contains 5, 8, 9, 10, 12, and 13. Second set contains 8, 9, 9, 10, 10, and 11. And they both have a mean or average X bar value equal to 9.5. You can check me on that, but my X bar, which is representing our mean, is equal to 9.5 for both of these sets. But which one of these sets differs less about the mean? We can represent these sets on a number line. I've drawn a dashed line through the 9.5 mean value and then put X's above each value from the data set. So here's what we have. We have kind of an example where things are very spread out. That's in this example on the left. And then on the example on the right, we have things much more condensed around the mean. The scores in the set or the data on the set to the left are much more closer to the mean. And so therefore they would have a smaller standard deviation, but we're going to actually learn how to calculate the standard deviation so that you're able to not only say that, but you can also prove it. Here is the list of the procedure from the book in order to find the standard deviation of a set of data. There's a very long formula that represents this, but if you follow these steps, you'll be able to kind of better figure out, it's a kind of a better way to figure out the standard deviation without having to memorize a large formula. So the first thing we want to do is we want to determine the mean of the set of data. So that means we find X bar. The second thing we do is we make a chart having 3 columns. We're going to have the data, so the information and the data from the set. The second column is going to be the data minus the mean. And then the third column is going to be the data minus the mean squared. So we're going to list the data vertically under the column marked data. We're going to subtract the mean from each piece of data and place the difference in the data minus mean column. We're going to square the values from the second column to get the values for the third column. Now, squaring these means that we're going to get values that are positive. So one of the reasons why we square our data minus mean is because when we subtract that, we might get negative values, and by squaring it, it ensures that we won't have any negatives, because a negative times a negative equals a positive. Number 6, we'll determine the sum of the values in the data minus mean column. Step number 7 will be to divide the sum obtained in step 6 by the values n minus 1, where n is the number of pieces of data. So when we are dealing with a sample standard deviation, we divide by n minus 1. Notice the little mark here. That's a side note, just to note that if we were looking for the population standard deviation, we would divide that column, the value we got from that column, by the value n. So then lastly, I know it's a lot of steps. Lastly, for step 8, we determine the square root of the number obtained in step 7. This number is the standard deviation of the set of data. So let's do an example. This asks us to find the range in the standard deviation for the following data set. Notice I picked a very small set because I don't want to have to do this with a lot of numbers. We're going to round our answers to the nearest thousands if needed. So first, we're going to find the range. That's our nice and simple task. The range is the highest number minus the lowest number. So that's going to be 6 minus 0. So our range is equal to 6. Now, so we've already answered part of the question. So I would like to say that we're halfway done, but we did the easy part. The harder part is the standard deviation, which I would probably argue is not half of the problem. It's probably 90% of this problem. So anyway, first we need to find the mean of the data set. So we have to sum the x values and then divide by how many there are. So that's going to be 0 plus 1 plus 3 plus 4 plus 4 plus 6 divided by there are 1, 2, 3, 4, 5, 6 values. So our n is equal to 6. So n minus 1, which we'll need later, is equal to 5. Okay, so our mean, our x bar value is equal to 3. So we have our mean. So now we can make our chart. We then list our data values. I do them in order from least to greatest. And now we find each piece of data minus our mean that we found. So that mean was equal to 3. So for the first one, we have 0 minus 3, which equals negative 3. 1 minus 3 is negative 2. 3 minus 3 is equal to 0. 4 minus 3 is equal to 1. 4 minus 3 is equal to 1. And 6 minus 3 is equal to 3. Now we take each of these values and we square them. So please remember that we're squaring the entire number. So when we do negative 3 squared, put the negative 3 in parentheses if you're going to use your calculator. Now, I hope you know that negative 3 squared is equal to positive 9. But if you need to use the calculator, any negative number, if the exponent is applying to that whole value, you need to make sure that the negative is included within parentheses. Your calculator follows order of operations, so it would do the exponent first and would only apply it to the whole number, the numerical value there. It wouldn't apply it to the negative. It only applies it to negative 3 if you put it in parentheses. Anyway, I'm going to continue on. And we have all of our values in that last part of our chart. So now we sum them together. So our next step was to sum these values. So 9 plus 4 plus 1 plus 1 plus 9 is 24. So I just took a second to label the steps in purple. So finding the mean was step 1, creating the chart was step 2, writing the data down under the data column was step 3, doing the subtraction of data minus mean was step 4. Squaring that difference was step 5. And then step 6 was to sum the values in that column. So we've done through step 6. So in our value at step 6 was 24. So for step 7, we take 24 and we divide it by n minus 1. N minus 1 we figured was 5. We did that at the very beginning. I have it in the top right-hand corner. So 24 divided by 5 is 4.8. Okay, so we did that division, which is step 7. And our last step is to take the square root of that number. So in your calculator, if you're using the TI-30X2S, you have the way you get to the x squared is you push second. The way you get to the square root is you push second, and then you push the x squared button because above the x squared is your square root button. So you would do that, and then you would type 4.8, and then equals. So let's do that. The square root of 4.8 equals fun times, 2.19089, etc. It keeps going. But we were told in the problem to round to the nearest thousand. So the thousands place, this is tenths, hundredths, thousandths. So we use the digit to the right of that one to determine does this value in the thousands round up or down. The check digit next to it is 5 or greater, so this rounds up to a 1. So this would be 2.191. I know that's really tiny, but hopefully you were able to follow along. And that is our standard deviation for the set. So we found the range to be 6. We found the standard deviation S to be 2.191. When we continue with the next section, we're going to be looking at the normal curve, and we have to determine some information about how many standard deviations certain things are away from the mean. And so being able to find and know what the standard deviation is really important. I'm going to suggest that you attempt this problem on your own. So I'm going to suggest that you pause for a moment and try and calculate the range and the standard deviation for this following set of test grades, and then go ahead and play and check your answer with my work.